Today we are going to discuss about two important thermodynamic processes, reversible process and irreversible process. First one, reversible process. A thermodynamic process is reversible if the process can be turned back such that both the system and the surroundings returns to their initial state with no other change anywhere else in the universe. For example, like this, if the system moves from the initial state to final state, initial state having pressure P1 and volume V1, and it undergoes a change so that volume and pressure changes to P2 V2. Clear, children? Again, so what is that process called? That is called a volume increases, no? So it is considered to be an expansion. On compression, if the pressure changes and returns back to the initial state without any change, now the system is said to be reversible. So this is the reversible process. Initial state, and after so many processes, if it come back to the initial state without any change in pressure or volume or temperature, and such a process is called a reversible process. Here a process is reversible only if it is a quasi-static process. Quasi-static, we know it is an infinitely small or infinitely slow process is called a quasi-static. So a process is reversible only if the process is quasi-static. We know quasi-static is an idealized notion. Okay. And here in a reversible process there are no dissipative effects. So there is no loss of energy. It should be 100% efficient. So there is no loss of energy in the form of heat or any other dissipative forces. Okay, so here there are no dissipative effects. So such a process is said to be reversible process. An example for a reversible process is a quasi-static isothermal expansion of an ideal gas taken in a cylinder fitted with a frictionless movable piston is considered to be reversible process. Here we can consider an ideal gas taken inside a cylinder fitted with a frictionless movable piston. Now let us place the cylinder on a conducting platform and imagine compressing the gas by slowly dropping some grains of sand on the piston. Every time a grain of sand is added on the piston, what happens to pressure? Pressure slightly increases. Volume of the gas decreases, but the temperature remains unchanged. Thus, each added grain of sand takes the system to a new equilibrium state. So, an isothermal compression of the system takes place quasi-statically because it is a very slow process. Now, the process can be reversed by slowly removing the sand grain from the piston, taking the system back to the initial state quasi-statically through an isothermal expansion. So, since the process takes place quasi-statically, this can be considered as a reversible process. Okay? But all processes in nature are considered to be irreversible. But since quasi-static process is considered to be an idealized concept, reversible process is also an idealized one. Now next one, irreversible process. A thermodynamic process which cannot be retraced exactly is called the irreversible process. Here the process involves dissipative effects like friction, viscosity, etc. Okay, so the process which cannot be retraced in the opposite direction, okay, retraced exactly is called the irreversible process. And here in an irreversible process there is always some dissipative effects. Energy loss is there in the form of friction, viscosity. Viscosity we will study in mechanics of liquid chapter. What is viscosity? Viscosity is the friction in fluid is called viscosity. Okay, so in irreversible process there is always some dissipative effects, loss effect. Example for irreversible process are cooking gas leaking from gas cylinder in the kitchen diffuses to the entire room. Can we bring the gas back to the cylinder? No. So diffusion process is not a spontaneously reversed process, hence it is an irreversible process. Then combustion reaction of a mixture of petrol and air. So combustion reaction mixture of petrol and air ignited by a spark. It cannot be reversed. Clear? Now expansion of gas, free expansion of gas. Now some more examples are rusting of iron, dissolution of salt in water, a body coming to rest due to friction, Okay, then if you want to transfer heat from hot body to cold body. So these are all examples for irreversible process, and hence we can say that most of the processes in nature are irreversible. Hence we can say that irreversibility is a rule rather than an exception in nature. In the previous class we have studied the first law of thermodynamics. First law of thermodynamics is the extension of law of conservation of energy. Okay. The first law does not tell us about the extent to which heat energy can be converted into mechanical energy. It also does not give any idea about the condition under which heat can be converted into mechanical energy. Okay, so second law of thermodynamics attempts to resolve these limitations of first law of thermodynamics. So now we can discuss what is the second law of thermodynamics. Second law of thermodynamics consists of two statements. First one is Kelvin-Planck statement. No process is possible whose sole result is the transfer of heat from a reservoir and the complete conversion of heat into work. So complete conversion of heat into work is not possible. Okay, so always there is some amount of energy lost as heat or some amount of energy used to increase the internal energy. Clear? So complete conversion of heat into work is not possible. So for any heat engine like petrol engine, diesel engine, steam engine, etc., efficiency cannot be 100%. Okay, so efficiency means work divided by output divided by input. Output means work divided by input means the quantity of heat supplied. So since the quantity of heat cannot be completely converted into work, efficiency of a heat engine cannot be 100%. So this is the Kelvin-Planck statement. No process is possible whose sole result is the transfer of heat from a reservoir and complete conversion of heat into work. Now the second statement is called Clausius statement. No process is possible whose sole result is the transfer of heat from a colder body to a hotter object unaided by an external agency. So we know that heat usually transfer from hot body to cold body. Okay, heat normally transfer from hot body to cold body without the help of any external agent. But in order to transfer heat from colder object to hotter object, we have to give some external agency. Only with the help of external agency, heat can be transferred from colder body to hot body. So that is the second statement. No process is possible whose sole result is the transfer of heat from colder object to a hotter object unaided by an external agent. So with the help of an external agency, we can transfer heat from colder object to hotter object. Without the help of any external agent, we cannot transfer heat from colder object to hotter object. So this is the working principle of a device called a refrigerator. Okay. Thus we have completed the chapter thermodynamics. Now we can do some numericals relating to the chapter. In thermodynamic process, 100 joule of work is done on the system and its internal energy decreases by 250 joules. Find the quantity of heat absorbed or rejected by the system. So here 100 joule of work is done on the system. Work is done on the system means work is taken as negative. We know that work done by the system is positive and work done on the system is negative. So here work done on the system. Work done on the system is minus 100 joules. Clear? Work is done on the system means volume decreases. Volume decreases means work done is negative. Now internal energy decreases by 250 joule. Internal energy decrease. Internal energy is represented by delta U. Internal energy decreases means that is also negative, minus 250 joules. So here work is done on the system, therefore negative. Internal energy decreases, therefore it is minus 250 joules. Now we can find out the quantity of heat delta Q. We have the first law of thermodynamics. What is the first law? Delta Q equal to delta U plus delta W. So quantity of heat is used for increasing the internal energy and remaining for doing work. This is the first law of thermodynamics. Okay, so here we have to find out delta Q equals delta U, substituting minus 250 plus minus 100. So it is minus 350 joules. So quantity of heat is given by minus 350 joules. Since quantity of heat is negative means the system rejects the quantity of heat. Okay, so we have to find out the heat absorbed or rejected. So how much quantity of heat is rejected? Since the quantity of heat is negative, that quantity of heat is rejected. The system rejects the heat. Okay children, if quantity of heat is positive, that means the quantity of heat is absorbed. Here, since quantity of heat is negative, that much quantity of heat is rejected by the system. Second question, an electric heater supplies heat to a system at a rate of 100 watt. If system performs work at a rate of 75 joule per second, at what rate is the internal energy increasing? So heat supplied to a system at a rate of 100 watt. We have the relation between quantity of heat, work and internal energy. What is the relation? From the first law of thermodynamics, delta Q equal to delta U plus delta W. We have first law of thermodynamics, delta Q equal to delta U plus delta W. Here quantity of heat supplied at a rate is given 100 watt. We can divide the whole equation by time. We can write delta Q by time is equal to delta T we can take is equal to delta U divided by change in time plus delta W divided by time. Delta T represents time. So quantity of heat divided by time is called what is energy divided by time called power. Okay, so delta Q by delta T is 100 watt. So here it is given as 100 watt equal to delta U by delta T, that means the rate at which internal energy is increasing, that one we have to find out. Delta U by delta T we have to find out, plus delta W by delta T means work divided by time. So that is 75 joule per second. Its system performs a work at a rate of 75 joule per second. So here it is given as 75. So what is the rate at which internal energy is increasing? Delta U divided by delta T is equal to 100 minus 75, that is 25 joule per second. So rate at which internal energy is increasing, rate of increasing internal energy, is equal to 25 joule per second. So why we have divided the whole equation by time here? Because in the question it is given as watt. Watt means energy divided by time. Energy divided by time, that means joule per second is called a watt. So here in the question itself it is given, rate is given, therefore we have divided the whole equation by time. Okay. Now next question, a thermodynamic system is taken from an initial state D to an intermediate state E by linear process as shown. Its volume is then reduced to the original value from E to F by an isobaric process. Calculate the total work done by the gas from D to E to F. Figure is given. Graph is also given. Pressure volume graph is given. Volume is plotted along the x-axis. Pressure is along the y-axis. This is the graph. So D to E. What is that process D to E? Pressure decreases and volume increases. That is a linear process. E to F. E to F means what remains constant there? Pressure remains constant, isn't it? E to F, pressure remains constant. That means E to F is an isobaric process. Then F to D, what remains constant there? F to D means volume remains constant. So it is an isochoric process. So here it consists of linear process, isobaric process and isochoric process. We have to calculate the total work done by the gas from D to E, E to F and back to D, the whole process. Okay, so we have to, during this whole cyclic process, we have to find out the total work done. So work done by the gas is given by the area. Okay, work is always given by the area under the pressure volume indicator diagram. So here what represents the area? DEF. This area represents the work done. So work done by the gas, is equal to area of triangle DEF. Okay, work done by the gas is equal to area of the triangle DEF. that is equal to, how will you find out the area of the triangle? Half into EF into DF, isn't it? Half into base into altitude, half into EF into DF. Substituting half into, what is this EF? 5 minus 2, okay, that is 3, into what is DF? DF equal to 600 minus 300, that is also 300. And simplifying, the answer is 450 joule. Okay, since it is work done, so the answer is 450 joule. So in pressure volume indicator diagram, work is always given by the area under the graph. So here work is given by the area of the triangle DEF. Okay children. An ideal gas is taken around the cycle A, B, C, D, A as shown. What is the work done during the cycle? So here this is a cyclic process. An ideal gas is taken along A, B, C, D, A. We have to find out the total work done. So we know that work done by the gas is equal to area. Okay. So we have work done is equal to area of the graph. What is the area of the cyclic process? A, B, C, D, A. Area of A, B, C, D, A. Area of the figure A, B, C, D, A. What is the area? Here AB, length into breadth we can take. What is length AB? AB is equal to, here pressure is P, volume V. Here at the point B, pressure becomes 2P. Volume remains same because it is a which type of process? Is an isochoric process. Volume remains constant. Along BC means which type of process? Pressure remains constant. No? So at the point B and at the point C, pressure remains constant. So it is an isobaric process. Along CD, what type of process? Along CD, volume remains constant. 2V, here also 2V. So it is an isochoric process. DA means what remains constant? Pressure remains constant. So it is an isobaric process. So it is a combination of isobaric and isochoric process. So how will you find out the total area? Here this distance AB equal to, what is AB? P. Okay, here it is pressure P, here it is 2P. So what is the length AB? AB equal to P. Area AB into BC. What is the length BC? Here 2P, here also 2P. But here volume V, here volume 2V. So what is the length BC? Length BC is equal to V. So AB into BC, and what is AB? AB is equal to 2P minus P is equal to P. What is BC? BC is equal to 2V minus V, which is 2V minus V, which is equal to V. So equals AB. AB equals P, BC equals to V. So work done is equal to PV. Okay.